Alright guys, we're going to look at this problem. This is number 5. I told you this is a good one because it's a kind of a lab-based thing. So here we go. Part A, we are supposed to describe a procedure the students could use to determine the charge on this disk at the very top here. So this disk is charged and we got to figure out whether it's negative or positive. And they give you a bunch of stuff. They give you some plastic spheres that are all the same. They give you a cloth that would give the spheres a positive charge, and they give you a cloth that would give the spheres a negative charge, and then something called a grounding wire. And a grounding wire is a wire that you would connect to the disk and then to the ground, and that would allow charge to essentially escape from the disk to the ground. So for part A, make myself big. For part A, here's my wonderful drawing. Here's your disk. We don't know what the charge of the disk is. Could be negative, could be positive, we don't know. We have to come up with they want you to write a procedure. So that's what the test will do, is part of the test will have you write things. So you have to write in a very clear way about how you would do this. So I would have some sort of we have one cloth that would give something a positive charge. So if I take a sphere and I rub it, that would give me a positive sphere, right? That I would like hold so that it wouldn't discharge. And then I take a different cloth and rub the sphere, and that would give me a negative charge, right? So now I have these two spheres, one's negative, one's positive, and then I would bring the spheres close, and one will attract, the other will repel. And the one that repels is going to be the same charge as the disk is, right? So, so in the problem, this is what you would have to do. And there's an example response. But yeah, you really need to use two spheres because that way you know whether this thing is negative or positive. There's no other way to do it. So you'd have to have the two spheres, you bring them close, and then you would feel a repulsive force for that sphere that's the same charge as the disk is. Alright, for the second part, I had to read it a number of times, so you may have to read it a bunch of times too. So they have these two disks, and they're on an insulating board, and the board has friction. And they want to know whether the same amount of negative charge is put on this disk each time it's rubbed with a cloth. And the only way to figure this out is to see how this disk 2 influences disk 1. So they're going to charge disk 2, and they're going to bring it close to disk 1 until disk 1 starts to move. It's going to be repelled, and then they're going to measure the distance at which that repulsion starts to happen. I had to read this a number of times in order to understand what the heck they're doing, right? Now, for this problem, the question is deriving an expression. Let me make this, so right here, I'm going to highlight this, deriving an expression relating something to something else. Let me make myself big. Right? So the key word here is derive. And so you're making something, you're creating your own formula. Formulas don't come out of thin air. And so what you're going to be doing is you're actually going to be using something that you know as like a starting point. And so this is how we do this. Is there are clues here. The first clue is that we're talking about things that are charged, electrostatics, right? We're talking about charging things. We're talking about things that are impacting other things. We have a force. We have movement. So these are some of our clues. And so because of this, some people might think, well, it's moving, so I might use kinematics, but if you look at the problem, there's really not a whole lot of information as far as velocity or time or A. We're talking about charges, we're talking about forces and things being pushed or moved. And so the equation that I thought of to start with is KQ over R squared, KQQ over R squared, which is Coulomb's law. I think that's the equation that you should start with, right? You have two charges because you have two disks. You know what K is? Coulomb's constant. R squared would be the distance between those things, right? So this is our starting equation that we could fiddle with, okay? Now, what they do each trial is that they are going to rub one disk, rub disk 2, and then they're going to bring it close until it just starts to move disk 1. That distance that that they're going to measure between disk 1 and disk 2, they call D, right? And then Q2 is the charge on disk 2. Okay? And there's going to be a force there, right? And this is the thing. Both disks are the same, okay? So this is my starting equation. Now, what's going to happen here is that we're going to be rubbing disk 2 a certain number of times. So what they're going to do is they're going to say, okay, well, Q2 would be disk 2 rubbed a certain number of times, which they called N. So you rub disk 2 N number of times, and that gives you a charge Q2, disk 1, okay? K is a constant. You can leave it or not. It's a constant. The distance, they're calling D, so instead of R, you can call it D. So it's D squared. Now, what happens here is they want an expression relating D and Q, okay? And electric force it could be something difficult to measure. And so what happens is that they're going to say that each disk is the same size, same stuff that it's made out of, and it's sitting on this insulating panel, right? And so when you start to get that first disk to move, and it starts to move, when it moves, it overcomes what's called static friction. In other words, for a brief moment, those forces are balanced. The static friction force will actually be balanced with the electric force. So the equation that they end up coming up with is actually an equation that involves friction. And it looks something like that. Make myself small. Let's see what they say here, right? So force friction K Q1 N Q2 over D squared. You may have to stare at that a bit. You get a point for just attempting to apply Coulomb's law, which is great. You get a point for indicating the force between the spheres when they begin to move is equal to the frictional force, because you can't get something to start moving until you overcome friction. But there are 4 points here. All right, for the final part, and this is that linearization that I was talking about. We're going to try to figure out what would the students graph in order to determine whether the same amount of charge is put onto disk 2. And so, I'll make myself big here. So what quantities would you graph based on the equation from part B? So here's our equation from part B, and it's got all this stuff in it, right? You're looking at essentially 2 things. You're looking at the charge and how many times the thing gets rubbed, right? So, and that's on disk 2. So pretty much anything about disk 2, Q2 N, right? N is the number of times that it's rubbed. Q2 is the charge on disk 2. Those are things that you care about because that's what you're experimenting to try to figure out. D would be the distance between those 2 disks when disk 1 just starts to move, right? So these are all variables that can change that we may care about and that we could graph. Now there are things that are constants that will stay the same, and I don't really take these into account because they're constants, which means we don't really want to graph these things. Force of friction is a constant here because none of the stuff changes. The disks are made out of certain stuff and it doesn't change, and that force to get the disk to move will stay the same. K, of course, is a constant. Q1 is the charge of that first disk, and we don't mess with that charge. It's a constant. So those are things that we don't care about. So we only care really about these things. So the question is, what can we graph here, right? So the idea is that we want to get this equation into a form of y equals mx plus b, right? And so what I did is I multiplied both sides by d squared. Cancel that out there. And I divide by force friction. The reason I'm doing that is because y equals mx plus b, y has to be by itself on one side, so I want to get something by itself on this left side. I got k q1 in q2 over force friction. Now, what are my constants? K is, Q1 is, force friction is. Those are constants. So I got d squared equals n times Q2, right? So I'm thinking I can make d squared could be my y. And then, I can kind of do what I want here. Let's say we could make a number of times rubbed the x, y equals mx plus b. I mean, I could do something like that, right? Number of times I rub something is an experimental variable, right? This is something that I'm doing. Rub once, then I rub twice, then I rub 3 times. So, right, that's something that I can graph. How far that disk moves is something that I can graph, right? Because that's data that I can get. Charge may or may not be, finding charge with the stuff that they gave us may not be something that I can experimentally get. So that's why I'm not going to have Q2 as one of the things that I graph. So I'm going to make d squared on my y-axis, and I'll make number of times rubbed on the x-axis, right? And that should give me a slope of charge, right? That is helpful, and that's what we want. Make myself small here. So what they do, it looks like they did n on the x-axis, they did d squared on the y-axis, right? These are tricky in the sense that, and especially to grade these, because there are usually more than one right answer. And if you look at the points here, 1 point is earned for drawing a best fit line, which means you'd have to draw a best fit line. 1 point is earned for what property that you're going to use. What are you going to graph? What does the slope mean? What does this say? 1 point is earned for describing the ways the property indicates whether the same amount of charge is deposited on sphere 2 each time is rubbed. So their example is draw a best fit curve. See if it's straight or not. There you go. A straight line would indicate that the same amount of charge was put on the sphere for each rub. And so this is kind of how these would work. My guess is there'll be a lab-based type question on the test, and so they may, like I said, they may have us do this linearization thing. I think this is a good skill, and I hope this helped.